Okay, so on page 3 from yesterday, we had made our interval from 1084 to 1386. We also kind of discussed, we said, when we run the test today, so that Andre puts on his tax return that he averages $10 on his tips, but the IRS thinks that it should actually be higher. So we would then, our parameters the same, but our null hypothesis was that mu is 10, and our alternative hypothesis that mu is greater than 10. All right, and we discussed right at the end of class yesterday, what do you think, so when we get done running this test, what do you think the conclusion is going to be? Are we going to reject or fail to reject the null? I bet we reject, so we'll see if we do. Why do you think we're going to reject? Good, this entire interval is above 10, so I bet we're going to end up rejecting 10. 10 is not in that interval. Okay, good. Well, let's look and see if that's what happens. So there were our hypothesis statements. This was a one sample t-test for means. The other one yesterday was one sample t-interval for means. I had said that wrong yesterday. Okay, so now we're going to start getting our test statistic. And these ones, I still want us to do these one sample problems, one sample phantoms and panic by hand. One sample phantoms and panic by hand. So let's do that. So we have to get a t-score. Okay, so here, you don't have to write this formula down all the time, but let's do that since this is the first time we're doing it. So to get a t-score, then we're going to have our x bar minus the mean of the x bars, okay, over that standard deviation over the square root of n. Okay, this is that sample standard deviation, which that's why we're having to use t curves and not z curve. T, not z. All right, so then filling in the data from yesterday, 1235 was the average that Andre got from his 8 tips minus our claimed $10. And then yesterday we had computed that 225 over the square root of 8 was 0.8. So this is a t-score of 2.94, not a z-score. Okay? So think about what that is saying in a picture. It's saying if this is the t-curve, not the normal curve, but if this is the t-curve, then here at 2.94 sample standard deviations above the mean is this t-value. P-value is going to be the area above because it's an upper tail. So we need to find this area right here in that upper tail. That's our p-value. The probability of getting that sample of those 8 tips, 12.35, or something more extreme if the average is 10. Okay, so what are we going to do to get this area? How do you compute this tail area? Yep, it's not norm CDF, but TCDF. From 2.99 to infinity, which is 99. 2.94, sorry. TCDF from that T to infinity, comma, degrees of freedom, which is 7. Okay. And that is an area of 0.011. So that's a pretty small amount up there in that tail, 0.011. Okay, so then we now finish out our phantoms. Our p-value is 0.011, which is less than alpha of 0.05. What will that make us do? Reject HO, since that p-value is low. Reject HO. So we do. And so now let's write our conclusion. It's going to be in 2 sentences. The first sentence is going to be about the null hypothesis. So my first sentence is, since 0.011 is less than 0.05, I reject that, and this is the HO, mu equals 10. I reject that mu equals 10. I like to let's do that one in letters. And then the second sentence in words, in context. All right. So the second sentence is about what? The alternative. So the alternative, do we have evidence or no evidence of the alternative? We do. So there is evidence to suggest that the average of Andre's tips is greater than $10. Okay, so that's where I'm putting in my context. All right. So in summary, I want you to do the one sample intervals and tests by hand, not just putting the whole thing in the calculator and plopping out a interval and a t-score. Okay, it's important to some fundamental understanding of what's happening still. And so I'm going to have you keep doing that. All right, now, we did not get to page 6 yesterday. That is this, problem number 8 and 9. So page 6, we actually have several problems to do for homework, and I want you to have class time to do some. So this one is actually going to be an extra stamp. It's not required, but you can do page 6 for an extra stamp. All right? So there you go. It is 2 of the tests. It's this one sample t-test for means on the top and on the bottom, and then you don't have to do the assumptions, so it's not too bad. All right, moving on to what we're learning today. So go on over to page 7. Okay, here's page 7. So today we're going to talk about the assumptions and how they're a little bit different and what happens to our assumptions now that we have T curves instead of a Z curve. Okay? First and foremost, can we conclude with normal model applies? No, because it's not the normal model anymore. It's not a Z curve, so we cannot conclude with the normal model applies. We're going to end up concluding with nearly normal model applies. Okay, because it's not quite, but it's nearly, it's the T curve. All right, now, let's first start right here at the top where we're familiar with this stuff. Random. Okay, this is old. It says stated or assumed to represent. But what did we add this year? We said, let's make it randomly what? Selected from the population. Randomly selected from the pop. Or what? Randomly assigned or randomly assigned to the what? Good, to the treatment groups. I'm going to have to fix my song now that that's different. Randomly selected from the population or randomly assigned to the treatment groups. All right. Okay, let's take a look at the independent condition. How does this look? Is this different? Sample size is less than 10% of the population. Is that the same? All good. That's the same. Okay, large enough is tricky because it all depends. Mean or proportion. Means is 30. Okay, so for n equals 30, the t distributions are safe to use even if we don't know the shape of the population. You know, the central limit theorem is about the shape. And it says if n is large enough, it doesn't matter the shape of the population. So even if the population is skewed, if n is large enough, the sampling distribution that'll go in our t distributions will be normal. Or in this case, nearly normal. Now, I have kind of a flow chart to better display this information that's right here in this paragraph. So I'm going to show you the flow chart, but you don't have to write it down because it's in this paragraph. But here, let's take a look at this. All right. So first thing, if n is greater than 30, then we're good to go, and the nearly normal model applies. Good? All right. So no problems there. Let's now address what happens if n is less than 30. Dun, dun, dun. Okay, so now we have to think a little bit harder if it's okay to do a test. What's our first option that makes it really easy? If they tell us what? Okay, good. If they tell us this right over here, if they say that the population is stated to be normal or approximately normal, then yay, we're good to go. Okay, so that's our hope, our next hope. All right, but sometimes we're not so lucky. Sometimes it's not large enough, and they don't tell us it's approximately normal, so we have this. The population is not stated to be normal. Okay, then here's the next thing that you look for. Do you have individual pieces of data, like a list of all of the pieces of data? Do you have the individual pieces? If you have the individual pieces of data, then you can examine them and see if they look pretty nicely shaped. If they look pretty good to go, if they're unimodal, symmetric, somewhat symmetric, and no outliers, I've achieved what I need. If you don't have individual data to check for this unimodal, somewhat symmetric, and no outliers, then essentially you do have to stop. Okay, that's probably not ever going to happen in here. Okay, I know you want to stop. If you had to stop, you would be happy actually, probably, and instead of sad. But let's look over here on this side. Let's say it wasn't large enough. They didn't tell you the population's normal. They do give you all the individual pieces of data. So here's what we're learning today that's new. We are going to make a dot plot or a histogram and see what that data looks like. And if it looks pretty unimodal, somewhat symmetric, and there are no outliers, then we're super pumped. Because if we think those little bitty numbers that we got come up pretty nicely shaped, then we are good to go, and we then know the population or the sampling distribution is nearly normal. If it's not, then of course you would stop. Probably not going to happen in this class, okay? Because why would they do that? Unless your question's leading you to that. Unless the questions is saying, are the conditions met to be able to run a hypothesis test? Okay, then that's up for your decision that it's not. All right, so then in conclusion, you would say the nearly normal model applies because we're dealing with t-distributions. Okay, so let's practice this. Here we go. The bottom of this next page here, we have this situation where Thomas Lane is a busy street that passes through a residential neighborhood. Residents there are concerned that vehicles traveling on Thomas Lane exceed the posted speed limit of 30 miles per hour. The local police sometimes place a radar speed detector by the side of the road. Have y'all seen those radar speed detectors? Where they tell you how fast you're going? Do you like those? Do those make you slow down? Yeah, I've seen them in construction sites too, because they say, don't speed, while these people are out here. Okay. All right, so the police hope that those drivers will slow down if they are reminded of their speed. Okay? But guess what? The local residents are convinced that such a passive method is not helping the problem. So they're not convinced that it's helping. So they wish to persuade the town to add extra police patrols to encourage drivers to observe the speed limit. So to help their case, a resident stood where he could see the detector, and he recorded the speed of 23 randomly chosen vehicles. Okay, so at this point I'm thinking 23. So what's my brain thinking? Not large enough. And then my brain's also thinking, why didn't you just sit there and get 7 more so it was large enough and then you wouldn't have this problem? But anyway, so we'll go with this. So 23 randomly chosen vehicles passing through a randomly chosen time and day. Do the data, and that is correct grammar because data is plural, give the local residents evidence that the average speed of the cars going through the neighborhood is above the posted speed. Look at what you are given. A list of all of the miles per hour of the car, okay? So first I want us to solve this problem, and then we're going to address the conditions. So what's our parameter going to be for this? Okay. Mu equals the average speed of the cars going through that neighborhood. Okay, mu equals the average speed of the cars going through that neighborhood. All right. Next is going to be the hypothesis statements. What will our null hypothesis be? Our null hypothesis is that mu equals 30. And our alternative is that mu is greater than 30. Okay, so unless you prove to me it's greater than 30, I'm just going to say the average is good. This is a one sample t-test for means. And then notice I did not do the t-score and the p-value by hand with, doing all that x bar minus the mean over the standard deviation stuff. That's because we had all of this, data, and so I need to teach you how you do that in your calculator. So you are allowed to do that. So get your calculator if you haven't gotten it, and if you have gotten it, what do you think you would do with a list of data such as that? Go put it in a list. Where is it in your calculator? Stat edit. Stat edit will get you to list 1, and I want you to put those 23 miles per hour or registered car amounts in your calculator. Yes. All right, so now that you have your data in there, here is how we do this. We go stat over to tests, and what do you think on the menu is what we're doing here? Okay, it's not a proportion and it's not a z. It is just the plain t-test, so it is number 2, t-test. Okay, so number 2. All right, now, here's the other thing. Whenever you get those of you who don't have, just have your own calculator, yours is defaulted to probably having this stats word highlighted, okay? But you would have that if they gave you the statistics such as the sample mean and the sample standard deviation. They didn't give us that. So they gave us individual pieces of data. So if they give you individual pieces of data, highlight this word data right there and hit enter. Now it will just take what you put into list 1 and use that to get all the information it needs. So the null hypothesis is what? 30. Your data is located in list 1 with a frequency of 1 because you just put them all in one for one. Okay, how about the tails? Is this a not equal to, a less than, or a greater than 30? Greater than. So highlight the greater than and then calculate. And so then that automatically gives you the t-score and the p-value. Okay, that one you can't really do by hand unless I made you put it all in the calculator and then go do it by hand. And I'm just not that mean, so. All right, so how are we doing? Did we all follow that and get it? Okay. All right, so then with a p-value of 0.13 comparing to the alpha of 0.05, we would fail to reject HO. So let's write our conclusion. Our first sentence in our conclusion is going to be about the null hypothesis. Since 0.13 is greater than 0.05, I fail to reject that mu equals 30. Okay, so I'm failing to reject that mu equals 30. If I am not rejecting that, then what am I saying about the alternative? Second sentence should be about the alternative. I do or I do not have evidence of the alternative. I do not. So, and we'll do conditions over here on the left in a second, but we're just working with this conclusion on the right-hand side here. There is not evidence of the alternative. There is not evidence that the average speed of cars going through the neighborhood is greater than 30. Now after we're done with that, we're going to talk conditions, which I have in this little blob over here on the left. So that's kind of the new thing. And look at there what you see. You see a picture of a dot plot. And so let's have a little discussion about that. All right. First two things are as they have always been. Randomly selected cars is stated. Okay. Randomly selected cars stated. Independent. 23 is less than 10% of all such cars. Okay, so those random and independent are good to go. But is 23 large enough? No, it is not. So 23 is not large enough. Therefore, what's our next line of defense? What are we going to check for next? Don't just start drawing a thing. Go look up there and see in the problem. And what did we look to see if the problem says? Go look and see if the problem says the population is normally distributed or even approximately normal. If so, woohoo! Then you write that down and you go on. All right. So I want to go through the process of making this histogram for you. And if you don't have enough room, there's space on the top of your next page, okay, that you can do this. So let's go through this process. Here we go. All right. So the first thing I do is, of course, I'm going to have to be drawing this thing, and you have to label. If you do not label, it is wrong, period, no ifs, ands, or buts. You know how this class is so much about context. So we're going to be recording their speeds, and then we're going to be doing the number of cars that are reaching those speeds. So over here is the number of cars. And down here on the bottom, I'm going to put amounts of their speed. So what will this be down here on the bottom? Their miles per hour or their speed or whatever of the car. All right, so let's decide how to put our numbers. Here's my technique. I take the highest value, which was 38. I subtract the lowest value, which is 21. That gives me 17. And I always want 5 to 10 bins, or 5 to 10 bars. So I usually, unless this is a huge number, I just kind of divide it by 5. And I get something that seems fairly like a normal number close. So what number do you want to use? What's a number close to what that equals? Let's do 3. Yep. So I'm going to make each one of my bins be 3 miles per hour wide. Okay, so let me tell you how I did that again. High minus low. I divided by 5 because I want to have about 5 bins, and I make it something pretty normal. All right, so I'm going to come over here, and I'm going to put my railroad tracks because I'm not starting at 0, and I'm going to start at 20. This line is the number 20. This next line will be the number what? 23. So the line is the number value, okay? The next line is the number 26. The next line is the number 29, and so on. 32, 35, and 38. Okay. Now so there are my bins. So each one of those, think of those as like a bar, will come up out of those spaces. So the first number is 29. Where will 29 go? It doesn't go on a line, it goes, but look, the line is 29. So if 29 is on a line, which bin do I put the 29 in? To the right. It goes to the right of that number if it falls on a line. Okay, the next number is another 29, right? So I'm going to do that and put another dot there. The third number is 24. So that goes in between the 23 and the 26. And see how I'm going to line these things up? The next thing, there are 4 34s. So those go in this bin. 1, 2, 3, 4. See how I'm evenly spacing them, and I'm making them line up with the other dots. So they're all having their own little same amount of space. Okay, I want you right now to go finish putting the rest of those numbers in the correct bin. Go do that. I feel like I got something different than I had gotten earlier. Is that right? Or do I have something missing? I think I have something missing in the 29 to 32, do I? Is there supposed to be one more in the 29 to 32? Oh, no, that's what I have over there, so that's probably right. Okay. All right. So there's my, what I have there in my bins. Okay, and so now what we have to do, the purpose of this is to say that the population this is coming from isn't too crazy to assume that nearly normal model applies. Do you think that that is so whacked out and so funky that that it scares me about what the shape of the population is? No, I'm liking this. And here's the things that you have to notate. That it is unimodal. These are the three things that have to be stated. It's got this name called homoscedasticity. And so instead of writing homoscedasticity, we're going to talk about it being unimodal, somewhat symmetric, and let's see what else. No outliers. So being unimodal, somewhat symmetric, and having no outliers. I mean, because it's never going to be perfectly symmetric. I mean, I would be surprised. And then, how do I conclude this thing? Nearly normal model. In fact, that used to be a line in my song. Must include the DF. Nearly normal model. T, 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 not Z. Okay. So in conclusion, here's what we did today. We did that phantoms where you had to show your work by hand and getting a T-score and a TCDF. Then we talked about the conditions and how what you can do if you're given the individual scores. There's still hope there, but you have to say it's unimodal, somewhat symmetric, no outliers. And finally, these are nearly normal models, and that's how you make a conclusion. So again, your homework is to, if you do page 6, then you will get an extra stamp. And then, but you have to do pages 10 and 11, okay? Have to do pages 10 and 11, and those are requiring the conditions. So there you go. I want to go ahead and walk around and help you and make sure you're good to go and good to start on that. Yes.